Dear friends, greetings of the day and welcome to the channel. I am Manohar Tatvavadi from Total Output Power Solutions. In this series of performance improvement, we are going to discuss about the AFBC boilers and the problems associated with. In this first video, we will go through a brief description of the AFBC boiler with respect to the fuel fired. Actual case studies we will discuss in our next video. Now we see a picture of the AFBC boiler here. In AFBC boilers, the coal is crushed to a size of 1 to 10 mm depending on the rank of coal and type of the fuel fed into the combustion chamber. The atmospheric air, which acts as both the fluidization air and combustion air, is delivered at a pressure and flows through the bed after being preheated by the exhaust flue gases. The velocity of fluidizing air is in the range of 1.2 to 3.7 meters per second. The rate at which air is blown through the bed determines the amount of fuel that can be reacted. Almost all AFBC bubbling bed boilers use in-bed evaporator tubes in the bed of limestone, sand and fuel for extracting the heat from the bed to maintain the bed temperature. The bed depth is usually 0.9 to 1.5 meters and the pressure drop averages about 1 inch of water per inch of bed depth. Very little material leaves the bubbling bed. Only about 2 to 4 kg of solids are recycled per kg of fuel burnt. The combustion gases pass over the superheater sections of the boiler, flow past the economizer, the dust collectors and the air preheaters before being exhausted to the atmosphere. The main feature of atmospheric fluidized bed combustion is the constraint imposed by the relatively narrow temperature range within which the bed must be operated. With coal, there is a risk of clinker formation in the bed if the temperature exceeds 950 degrees centigrade and loss of combustion efficiency if the temperature falls below 800 degrees centigrade. For efficient sulfur retention, the temperature should be in the range of 800 to 850 degrees centigrade. Now the features of the bubbling bed boilers. Fluidized bubbling bed boilers can operate at near atmospheric or elevated pressure and have these essential features. Distribution plate through which the air is blown for fluidizing. The immersed steam raising or water heating tubes which extract heat directly from the bed, and the tubes above the bed which extract heat from the hot combustion gas before it enters the flue duct. This picture in general shows the construction arrangement of an AFBC boiler. The boilers range from 10 MW to even more than 250 MW. Fuels are also different for these boilers. The admission of fuel inside the boiler may be either over the bed or under the bed. I will see what is fluidized bed. When air or gas is passed through an inert bed of solid particles such as sand supported on a perforated plate, the air initially will seek a path of least resistance and pass upward through the sand. With further increase in the velocity, the air starts bubbling through the bed and the particles attain a state of high turbulence. Under such conditions, the bed assumes the appearance of a fluid and exhibits the properties associated with a fluid and hence the name fluidized bed. If the sand in a fluidized bed is heated to the ignition temperature of the fuel and the fuel is injected continuously into the bed, the fuel will burn rapidly and the bed attains a uniform temperature due to effective mixing. This in short is fluidized bed combustion. While it is essential that the temperature of the bed should be at least equal to the ignition temperature of fuel, and it should never be allowed to approach the ash fusion temperature of around 1050 degrees centigrade to 1150 degrees centigrade to avoid melting of ash. This is achieved by extracting heat from the bed through the evaporator tubes immersed in the bed. Now, the mechanism of the fluidized bed: if the gas velocity is too low, the fluidization will not occur, and if the gas velocity becomes too high, the particles will be entrained in the gas stream and lost. Hence, to sustain stable operation of the bed, it must be ensured that the gas velocity is maintained between minimum fluidization velocity and the particle entrainment velocity. Here you see the bed. You see the fixed bed with the sand, then you see the bubbling bed where the fuel air is supplied, and then the turbulent bed. Generally, we are supposed to operate in the regime of bubbling bed, but invariably we may land in the region of turbulent bed, where even the coarser particles are seen getting out of the bed. Now, the bed material. In a fluidized bed combustion system, the fuel bed material is the source of particles. In the case of coal, the burning particle and the burnt particles are the main contributors which decide the fluidization behavior in the bed. The bed material which is used for startup of a bed may be particles which have been sieved from the ash obtained from fluid bed combustor, or it is generally sieved river sand or the sieved crushed refractory bricks. When you use sand as the bed material, particles less than 1.5 mm should be used. These particles are generally round in shape. When the sand particle happens to be on the higher size, we can notice that the sand is sharp in nature. Such sand particles are found to be erosive when the bed is not properly fluidized. It is not necessary to remove the finer portion of the sand. The sand size range of 0 to 1.5 mm gets the best combustion of fuels in many installations. Sand is practically a crystallized material and does not have pores. Crushed refractory. When you use it as a bed material, the refractory bricks are made from recycled bricks and fresh refractory clay. The old refractory bricks dismantled from the ore melting furnaces and many other refractory furnaces are crushed to -3 mm as a part of raw material preparation in the refractory manufacturing industry. The refractory rock prepared in this way is screened in a 20 and 8 mesh, and the material that is lying between is used as the bed material for the fluidizing bed combustion. This bed material is found to be less erosive as the density of the material is lesser as compared to the sand. The size range is from 2.35 to 0.85 mm, corresponding to mesh numbers 20 and 8. Higher size has been permitted here as the particle density is lower due to presence of pores. Fuel sizing. Coal. Even if sand or refractory bed material conforms to required size range, over a period of fluidized base combustion operation, the entire particles are going to be replaced with the ash particles generated from fuel. Thus, the fuel sizing is very critical for the trouble-free AFBC operation. Ignorance to maintain the screen system at the coal handling plant can lead to accumulation of oversized particles. Once the oversized particles are accumulated, the bed goes for spouting. Even the heavier particles get thrown out of the bed. The loss of ignition would go up if the furnace residence time is less. If the coal is reactive with high volatile matter, the unburnt in ash may not go high. In the case of underbed firing, the erosion of bed coils is associated due to violent turbulence at fuel feed points. Smaller particles have more surface area to conduct the heat to bed heat transfer surfaces. The generation would come down as the fuel particle size increases. Now the fuel size. If it is a biomass, then in case of agrofuel such as rice husk or de-oiled bran, groundnut shell, the ash from the fuel does not contribute to bed particle size. Whatever the bed material used gradually disintegrates and the fines go out of bed. Regular addition of bed material is required in order to maintain the bed height. In husk-fired boilers, stone ingress that has to be looked into because stone ingress in husk-fired boilers is well known among old installations. More drains have been added in some cases to bring out the stones. The stone removal by mechanical screen system is not effective. Only one way to get the best from these combustors is to resort to frequent draining and recharging the screen bed material. Fine sand is the right option for the husk-fired boilers as bed material as the disintegration of the refractory type bed material could increase the operational cost. In case of de-oiled bran fired boilers, they experience peculiar problem of heavier particle generation due to melting of ash. De-oiled bran ash melts and agglomerates to over the sand or the bed material. More sand will be required to offset the bed particles becoming heavier. In general, agrofuels are having lesser density as compared to the bed material and they try to leave the bed earlier. Using finer material helps to achieve a good bed expansion and binds the fuel particles better. Now the firing of dolachar and coal together. Dolachar and coal are fired together in boilers used in sponge iron industries. The dolachar contains iron particles which are heavier. As one can expect, the bed can have segregation of particles to the bottom of the bed. In many cases, the operators ignore this. Once a bed lands into segregation of particles, there is no way out in case of a flat distributor plate design. Only open bottom design can pull out the oversized particles which settle down at bottom. Alternately, sloped distributor plate with many drains can help to control the particle separation. Particle separation, when takes place, preferential erosion of bed coils is seen. In these combustors, the generation of bed ash is also more. We may not find a requirement to add bed material for a long time. Except for a fresh startup, we may not use iron-free bed material. Bed coils in these boilers call for early replacement and the availability of the boiler is greatly disturbed due to the unscheduled shutdowns. In underbed system, the erosion of bed coils is localized, whereas in overhead the erosion is not so provided we keep removing the heavier lot. If the heavier lot is allowed to accumulate, the bed coils erosion is of different kind. The coil is seen eroded in between the studs too, as in photograph. There is a gross erosion of bed coil. All these troubles are related to iron accumulation. Here you can see in this photo, you can see the erosion of bed coils because of the dolachar and the DOB has been fired in this. You can see the erosion, you can see the eroded. The solution for this dolachar plus coal fired boilers, the solution could be a continuous bed ash iron removal system. The bed ash must be cooled and discharged to an automated magnetic separator system and oversized screen system. The screen bed material should be recharged to bed through a bed material silo and feeder system. It is advised to resort to continuous bed ash removal and recharge system. So these are some of the details about the AFBC boilers and the fuels fired. We will discuss the case studies and some problems with solutions in our next video. Thanks for watching. Like, share and subscribe. Total Output Power Solutions.